been asked to elaborate a little bit on the problem of a type that's similar to what's on your test. So here's a problem. I want to use a power series to find the exact solution of the integral from 0 to 1 of x minus sine x over x cubed with respect to x. I want to express my answer as an infinite series. Then I want to write down an estimate of the integral in decimal to within 1/1,000,000th. I want to write down a number that differs from the true value of this integral by no more than 0.000001, or 10 to the minus 6 if you like scientific notation. In any subject, we have to assume that we know some background material, that facts don't exist in isolation. The integral involves sine of x and combining sine of x with other simple things. So if you'll remember, we have a power series for sine of x. Sine of x is x minus x cubed over 3 factorial plus x to the 5 over 5 factorial minus x to the 7 over 7 factorial, and then so on and so forth. This infinite power series converges absolutely no matter what x is. Absolute convergence means we can treat these things as though they are polynomials. As a result, x minus sine x is x minus whatever sine of x is, x minus x, the x to the first power terms cancel out, minus x cubed over 3 factorial, minus x to the 5 over 5 factorial, minus x to the 7 over 7 factorial, and then continue this pattern. This is a power series that represents x minus sine x. If you'll notice, every term has at least a factor of x cubed in it. That'll be important to us, because the thing that we're integrating is x minus sine x divided by x cubed. So take the series that we just obtained, divide each term of it by x cubed, and you'll find out that x minus sine x over x cubed is 1 over 3 factorial minus x squared over 5 factorial plus x to the 4th over 4 factorial, and so on and so forth. The integral that we want to do then is the integral from 0 to 1 with respect to x of x minus sine x over x cubed. Notice that we do have a problem at x equals 0, but as with some examples we've looked at previously, there's a removable discontinuity. I'm going to pretend that there isn't even an issue. We'll integrate one term at a time. The integral of the constant 1 over 3 factorial is 1 over 3 factorial times x, minus antiderivative for x squared is x cubed over 3, don't forget about the 5 factorial, x cubed over 3 times 5 factorial, plus x to the 5th over 5 times 7 factorial, minus x to the 7 over 7 times 9 factorial, plus x to the 9 over 9 times 11 factorial, and so on and so forth. Take the antiderivative that we just obtained and evaluate it at 0 and 1. When I put 0 in for the x, all terms are 0, I ignore them. When I put 1 in for the x, all powers of x are 1, So every place I see an x or an x cubed or an x to the fifth and so on, I'm just going to write a 1 down instead. The exact value of the integral is the value of this infinite series. So the first part has been taken care of. Observe that that is an alternating series. If I were to calculate this term minus that term plus this term and stop, the alternating series theorem tells me that the error that I've committed is no bigger than how large the next term is. So we'll do some experimenting. What if I kept all the terms out to the 1 over 7 times 9 factorial term? The error would be no more than 1 over 9 times 11 factorial, which is 2.7 times 10 to the minus 9. That's 2.7 billionths. That would certainly achieve our goal, but it's probably overkill. What if I only kept the 1 over 3 factorial and the 1 over 3 times 5 factorial? Then the error is no worse than 1 over 5 times 7 factorial, and that's 3.96 times 10 to the minus 5. The alternating series test does not guarantee me then that the error is less than 10 to the minus 6. What if I kept this term, and that term? The error is no more than 1 over 7 times 9 factorial, which works out to be 3.96 times 10 to the negative 7. That's less than 1 millionth, which is 10 to the minus 6. So to get sufficient accuracy, I will keep this term, and that one to achieve my estimate of the integral. Summarizing, keeping those three terms, the number that I get differs by the true value of the integral by no more than 1 over 7 times 9 factorial, which is less than 1 millionth. To within 1 millionth, the value of the integral is that number minus that number plus that number, which, getting out the calculator, to within 1 millionth, the value of the integral is 0.16392855714. Hopefully this provides enough information for you to work the problem that you have. Everyone, have a good evening.